Hey guys, I made this video here to share an aha moment that I had this weekend making a GeoGebra app for my integrated math students on constructing a reflection point with compass and straight edge, but I wanted to do a GeoGebra app too so they can get both hands-on and computer practice. So I kind of had this thought when I was making it of connecting, because my brain's thinking about how I can build off this. Ultimately, what I want to get my students to know is that the slope of perpendicular lines are opposite reciprocals that we teach, and I'm using reflections to do that. So I really kind of want to share this idea or this thought, process, because it's doing a really good job of connecting geometry to algebra. So in my opinion, this is kind of what we have to think about when we think integrated. Why do we, just because we teach geometry and algebra doesn't make us efficient. We just reorder, what we teach. But if we can figure out a conversation that combines the GeoGebra reasoning to algebra concepts to build the actual concept base of our abstract thought, because algebra is just abstract and kids have a hard time with that. Geometry is really good with visuals and reasoning, so our logic base. So this video is going to kind of show you the connection there. Also, I went to a flipped classroom seminar in Billings, and so I'm practicing some techniques that I learned from the seminar. So I kind of hope you like what you see, and if you do, maybe it gives you some ideas here. And please feel free to ask questions or just let me know also what you thought about the video. If it's not good, I'm kind of practicing for my students on you guys. So this is my first video I've made, and I've done a bunch of retakes, and this has taken me a long time, but I think I'm getting better at it. So let's kind of see how it goes. So really the whole point of this video is, why do we care about function notation? So when I thought about function notation, and how are we going to connect function notation to reflections, and that's just a little glimpse into my mind here. To keep the video short, I'm going to talk really fast, and if you do have any questions about like what I'm talking about, if you're still kind of confused but you're interested, please feel free to ask me, and I'd love to talk to you about it. But GeoGebra is a connection of how I kind of thought about a really good use and allowing kids to use GeoGebra, maybe follow steps to create an app, or follow along with me in class to create an app on how we can create function notation based off of 2 points. But before, these are just some concepts of what I taught about when I taught function notation. These are the two main things that I talk about here. One, it allows us to be specific when we're identifying specific graphs when there's multiple on the coordinate grid. So we can use the labeling to help us be specific on which ones we're talking about. Also, it gives us an efficient statement that shows us input and output value. So for an example, like if we let f of x be 2x squared minus 1, let's evaluate for f for 4. So the notation tells us input output. I like to connect it to ordered pairs that also are just another notation of input output, but we use this for graphing, okay, where function notation can just give us a nice precise, here's the output 31 when we input a 4. So it shows us that conditional logic too, of if x was 4, then our output's 31. But now I kind of realize after playing around with GeoGebra that there's a lot more to function notation, and when we talk general, I think that this would be a good activity to get our students to work with. So I'll show you how we can make an app on function notation based off 2 points, and compare it to a line here in GeoGebra for a sec. But let me show you reason number 1436 of why GeoGebra is awesome. So I'm going to just kind of connect to you the concept flow of how we go from how I kind of went from creating a reflection app to function notation. Okay, so here's my GeoGebra app that I wanted to show with my students. I have a line of reflection here, and I have a point that I want to reflect, my pre-image. And again, I'm going to go fast here, and if you want specifics of the GeoGebra side of it, feel free to ask me and I'll help you out. So anyways, we're a couple weeks into reflections in class, so there's a lot of build up to this conversation and this construction, but I'll just kind of give you what we are going to do in class. When students have a line or they draw one by pencil, they don't really have 2 points, the 2 points that define the line showing. So I just want them to draw 2 points on their line, like A and B here. They're going to take their compass tool, they're going to make 2 circles centered at those points that go to our pre-image. The pre-image is on both circles, and we've talked a lot of reflections and symmetry to where now their eye can see and really confirm, I think, in their head that this has got to be where the reflection point is going to be or go. So now I always like to show too the under the hood stuff here. That's what I always say in my class of why the construction works. So if we connect these points with segments, then we get a kite that gets formed, and we've already taught kites and properties of kites, but now with this construction, really a kite's getting constructed, but we're using that vertex to be our connection to reflections, because that line of reflection is really cutting that kite in half, and we can talk about congruent point or corresponding points, congruent angles, congruent segments, all that good stuff. The properties of kites we can now talk about in just with reflections. So that's kind of what I wanted to get them to do. The connection to algebra, I want them to know the equation of the line or find the equation of the line and get to where the line that connects the pre-image and image point, the pre-image and the reflection point, that line there, is perpendicular to our line of reflection, which we know that's a property of our reflections right now. So they can get to opposite reciprocal slopes here. That's what I want to get to. So then what I was kind of thinking about when I'm making this app, I thought that I kind of wanted to use a slider to slide an input value around, or maybe use sliders to move C around. I don't know. I was just thought sliders, which then made me think about, well, maybe I want some text to show the input value that I'm putting in and the output that I'm getting out, and I can see some relationship in the ordered pairs might help me understand how to find this point, exactly. So to do that, we need function notation. But the problem is with what we got right now, and let me hide the geometry here, that we don't need this anymore. So let's just talk about the line here. So I'm just hiding all the things I don't want to look at right now. Just look at this line. Okay, now the thing about it is we have the equation of the line, but we don't have any way with this notation right now, the y equals notation in GeoGebra, to take a specific input and tell me the output. But more importantly, if I just want to pull out an output value, I have to know what my input is that gave me that output based off of our equation. So function notation with the f of x nature allows me to, in GeoGebra, to just pull out that output value, which is f of x, and depending on our input. Okay, so how do we get function notation? So if I hide this line, I want to write in this input bar down here, f of x equals something that takes these movable points coordinates here for a and b. This is like 0.1, 0.2. And make the line that connects those 2 points. So we have to think general here, the general equation of a line. Okay, so our general equation of a line is y equals mx plus b. We tell the kids that slope equals this equation. Take the difference in your y coordinates divided by the difference in our x coordinates. Okay, and if we wanted to have an expression for b, all we have to do is subtract this mx term over on both sides here. So b really equals y minus our slope times x. In GeoGebra, so this is what we teach in algebra, so let's connect that to GeoGebra. In GeoGebra we have 0.1, 0.2, but we're calling them a and b. So this notation, x of a, so this is a bunch of function notation, which is going to reinforce if we have students typing this in and getting used to typing in a little bit of code, I think that they can really understand some of the general properties that we have in algebra, make that connection. Okay, so anyways, the coordinates of a, the x coordinate of a, the y coordinate of a, here's b, the x coordinate of b, y coordinate of b. So if I want to find slope, I'm just going to generalize that for GeoGebra. So slope is going to equal this formula based off of our y coordinate of a minus y coordinate of b. y coordinate of 0.2 minus 1, and same deal with the x coordinates. Okay, so now to find the b, this is what I do for my students. I tell them that once we know slope of the equation, and I know an input and an output pair that comes from our ordered pairs, so my students know to look at an ordered pair and know that they're input-output, that we can just plug in the x-coordinate of one of the points and the y-coordinate of that same point, and we can solve for b. So this expression right here is really that idea here that I'm taking the x and the y coordinates of point A, just one of our points, so I'm taking point A. So then we would have the y coordinate of A equals, so that's the output of A, our slope, which is this equation, times the x coordinate of A plus B. Therefore, if we subtract this term over, B's got to equal the y coordinate of A minus slope times the x coordinate of A. So now what I'm going to do in GeoGebra is I'm going to type these two expressions in, and I'm going to just get GeoGebra to hold the value of m, our slope, and b, our y-intercept, based off of our points A and B, and then I can just type a nice easy equation here, and I'll show you. Okay, so here's our GeoGebra app. We got points A and B here, so I'm going to get rid of this f of x, and I'm going to call some variable m, that's our slope. It's going to equal, I'm going to put in parentheses here, the y coordinate of A minus the y coordinate of B. Outside of the quotes, I'm going to divide that by, and again, I'm just going to group up my numerator denominator here with the x coordinate of A, right, minus the x coordinate of y. I've made this video a few times here, and I'm trying to cut down time, by the way, and I have about 3 more minutes on this screen capture app. It only gives me a 15-minute cap, and so I will have to make a second video just to continue where I'm at here. So if this video stops, just click on the second link that I gave you in the email and just finish the video if you want to. You don't have to, but anyways, I'm just going to continue. So this general formula here that I plugged into GeoGebra, if I hit enter, notice m is my slope value. So wherever I move A and B, notice m, maybe I have a slope of -1, right? Down 1 to the right 1. So here's my slope value, -1. Now I have to plug in the value of B, which we said was our y coordinate of A. So I'm going to say B, our y-intercept, is the y coordinate of A minus our slope, which I now have as m, so I can just use m now. So m times the x coordinate of A, right? The input and the output of a point. So now, when I hit enter, then we get a b value of 5 here. So what I can do then is type f of x equals our slope times x plus b, the general form of our equation, and we have m and b solved for, right? So again, it's a deeper conversation, probably not a freshman, but who knows, conversation. But here's our general form of a line, right? Just in function notation. So when I hit enter, there's my function, my line here. So whatever a and b do, oops, why'd that go away? So wherever a and b go, then that line's going to stay with it because we use the general coordinates of whatever these points are. So it can help build some concept for our students. Okay? And actually, I think that I'm done here. But I wanted to kind of reinforce some ideas here. Geometry allowed me to think about this property here to create an equation based off function notation that took the general properties and equations that we teach in algebra, and now we can use it so that can help students understand why we want to use function notation. So I kind of panicked in the video, sorry. There's a minute left here, so I'm going to end this video. If you want to see the connection of how I'm going to connect opposite reciprocals, it's pretty easy. I just need to do a second video just because I need more time. So anyways, the second link now in the email will be the extension of how I will just show opposite reciprocal based off of a point that we want to reflect and its reflection point. Thanks, guys. Hope this makes sense. And please let me know if you have any questions. Thanks.